welcome to this presentation, shaving of bytes at any scale. I will be talking about some space savings that we could realistically get within various subsystems of PostgreSQL. Let's start with an introduction. My name is Matthias van Meent. I'm a Postgres developer from the Netherlands. My career path was quite interesting. I started out as a front-end developer, went basically directly full stack due to the nature of the startup I worked at back then. That went into infrastructure and DBA in 2018 and eventually became a Postgres hacker due to my job as well as the issues that I found in Postgres. Not a lot, but when you find them, you try to fix them. And since 2021, I've been full-time employed on a Postgres-related job. Yeah, that's me. What I will be talking about are these 4 basic items about implementing savings in the catalogs, in table storage, in WAL, and in Toast. There are probably more systems, but these are standout items that I think are quite interesting and we can get real significant improvements there. As for the catalogs themselves, what I will be talking about, PG node tree, PG attribute and PG type information, and more aggressive Toast targets. As for the catalogs themselves, they are usually not that large, but as everyone needs to have a catalog, it can be quite significant overhead if you have a lot of small databases or just template databases. It can get quite expensive quite quickly, especially if you're working on large scales. An empty database starts out with some 7 megabytes of data. That's actually quite expensive if you're working with millions of databases. So, as for the PG node tree, it is an actual type that is used in our catalogs. It is used for serializing nodes, for instance, default expressions on columns and expression-based indexes. They store the expression of what the index is all about, how to produce the index values. And it can get really expensive because they are used for both storage and it uses the same format for both storage for long-term systems and for debugging. So it's currently a textual format which is extremely verbose. Compare it to JSON, but it's their own misinterpretation of a Lisp syntax. It can be quite difficult to parse to process. I only recently found out there are actual debug functions which reformat into something that is more readable. But they are not user visible, and when you query the catalogs for instance, the PG rewrite catalog, which contains a lot of this, you will notice that it is very verbose and difficult to find the exact thing that you're looking for. And because there is no nice way to query this, it's also just it's not a great format, both for user debugging and for the general storage. So we should be able to improve it significantly. I have been working on a replacement where we replace it with a binary format, where a new read-write infrastructure is implemented with a new binary format rather than the very verbose, not quite JSON, but also format. The initial tests show a significant reduction in plain text storage, which should be even better after compression. And also the performance of writing it out and reading it out is quite significantly better. And using the same infrastructure, also a textual format can be relatively easily implemented. It is not yet ready to be published on the hackers list, but initial tests show really good improvements. And it would also allow improved debugging experience with the catalog data, because implementing a JSON writer of node structures is also just as easy as implementing the binary format, using just the metadata of how does this node type, what's the structure of this node type. I've been working on that. I hope to have the patch on the hackers list soon, but there are still some issues that I'm trying to figure out. The other issue in the catalogs that I was planning to talk about is the PG attribute, and basically anything that is related to names. On head, the minimum size of a PG attribute column is 104 bytes of payload data. It's actually quite a lot, and when you look at that, you see that the name data, the name is actually more than half of the data. It's very expensive. We should really get to detaching the on-disk format with the in-memory format, so that we can store names in efficient ways without wasting so much data on just the empty bytes, so that we can support longer names. Because if I want a longer name now, I have to increase name data length, and that increases the overhead of everything. It's very wasteful. We also have some bytes from the PG type column, which we basically only have in those columns which we need to have in PG attribute, because it is possible that you drop the column, but the data still remains, so you need to be able to deserialize it. But once you've dropped the column, the PG type the dependency on the PG type entry in the PG type table is also removed. So we need to copy over the attribute length and value, by value and alignment into the PG attribute table. However, we don't need it when the column is still visible. So in most tables, you will have more columns that are visible than dropped. And we should just reuse the PG type values whenever possible, rather than always having the attribute length by value and aligned. It saves 4 bytes, but it's still 4 bytes in every column that we have in any relation, which is quite wasteful. And also, we have a lot of flag bytes. I counted them, 5. If we put it in a single flags field, we also have another 4 bytes savings. I don't have the performance. I don't know the performance impact, but it sounds like a really trivial ID for the bytes for the savings that we can attain by that. Also, when we change the name data length to be in variable length system, a lot of the other catalog tables will also get a reasonable decrease in size, because the 64 bytes is basically never used by most users. I also tested around with putting a more aggressive toast tuple target on the catalog tables. Especially in PG rewrite, it saves 10% or so of the current table size. It's not a lot, but it's also, on the whole of the system, it can be quite significant if you really want the last data out. And it is a bit of a mixed bag. You will see that some attributes are compressed earlier than they would normally be compressed, which does mean that some accesses will be slightly slower. On the other hand, you will have less data in toast tables, which means that the accesses of other columns data will be much faster, because you don't have to go through other tables to access it. So it's a trade-off. I think we can make the trade-off, but someone needs to decide on that. Yeah, it depends on whether we really want smaller catalogs. Some cases it may make a lot of sense. Okay, next up is table storage. These are the items I will be talking about: visibility information, physical column order, compression and columnar. and index data. While index data is not strictly table storage, it is similar enough that I think we can just talk about it on this item. As for visibility information, every tuple has a 24-byte, technically 23, but 24-byte tuple header, of which 18 bytes are visibility information, plus 15 info mask bits. It's actually quite a lot of data, and it's kind of it's basically wasted data while the tuple is actually frozen. I think there are. So if we put all that visibility information in a separate fork, where we can move the visibility information around and remove it when the tuples are frozen, we can retain only, say, 2 bits of information in the tuple header itself, namely, is my tuple fully frozen, or is my tuple potentially deleted, or that kind of stuff, so that we know, hey, my tuple, I should go look for visibility information elsewhere, or I have this visibility information already because it is frozen, so I will never have to look at another fork, which means that we can remove those 18 bytes plus 15 info bits from the tuple header and save a lot on storage. A basic calculation shows that we can increase the maximum number of tuples on a page by a very significant margin. The second item is physical column order. Right now, we can lose a lot of padding, a lot of storage based on padding information. For instance, when you have a Boolean column followed by a bigint column, you can have up to 7 bytes of alignment losses because the Boolean is 1 byte, and the bigint will be put at the next alignment border for the bigint column. On 64-bit systems, that is the next multiple of 8 bytes. So after 1, you have 7 bytes of alignment, which is quite expensive. If Postgres itself was smart enough and was capable of putting columns at any place in the order in the tuple, then we could just put the bigint column at the start of the tuple.
We don't actually need to have the padding in the table for anything that is a by value type because we don't ever actually use it except for catalog tables that are struct mapped. So you can actually we don't even need to reorder anything because we read it into, while deforming into somewhere aligned.
I am not sure that is always correct. But okay.
Tables it is.
Okay. Anyway.
Sorry, are you saying you don't have to align, like declare your columns in a specific order to pack them?
In theory, Postgres wouldn't need to use padding in those places. Not that it's not implemented, but we could just get rid of that padding, except for like.
We still need to do this if we're going to. Like we still should align, like he's saying. Do your try and align things in 64-bit blocks
until Postgres is improved. Yes.
Okay. It's the same thing.
Anyway, the point is that there are alignment issues and alignment losses, and we should at some point get to fixing that, because it can be really expensive if your developers start adding columns willy-nilly, and then suddenly you have another few bytes of alignment losses. That's very wasteful. One issue with that, though, is it's really easy to do that during table creation time. It's much more difficult when you just add another Boolean column and you notice, hey, there is a potential gap where I can put that column. But you can't just put it in between because there could already be other tuples which have that information there. So if you use, we could use the heap number of attributes value to also double as a tuple layout version, which would allow us to determine, hey, this old tuple has the older layout without an extra Boolean in between. The newer tuple has a newer layout with the Boolean with the additional Boolean in between column 1 and column 2 here, in case we are having issues with alignment losses. Another item is table storage. It's we currently store basically all data uncompressed on disk, unless it is toasted, which means only variable length data is compressed. But in quite a few cases, tables contain a lot of similar data with a lot of locality and on the same page. Right now, we don't have compression at all. Compression is also relatively difficult to get correct because, as mentioned earlier, we need to have the visibility information and we need to have the space for visibility information on the same page so that we can actually delete a tuple without overflowing the size of the page. It's really weird to have to think about that, but if you can't delete the tuple, then that's an issue. But you could realistically compress the data sections of all tuples all at the same time without compressing the visibility information. And yeah, we could do that at the page level. We could do that after splitting out the columns and then do the columnar compression at the page. There are various schemes possible, but it's really wasteful that we don't have even the option of compressing page level data. Even MySQL does this, or at least has the option to do this. Yeah, they have larger pages, but also it shouldn't be that it is difficult, but it isn't that difficult to at least give it a try. I know there are companies who have implemented this in their own fork of Postgres to varying levels of effectiveness. We should try it out at some, yeah. This also applies to indexes, or especially to indexes, because indexes have a lot of similar data on the page, or at least that is usually the case. Hash indexes may be less accurate, but most indexes, it's quite similar data. So we should really check out if we can compress the data of index pages much better. That brings me to the next item. The data is essentially always co-located. We know what kind of data is in every index column. That's basically what the AM is all about. So we should just do better compression. We should use less data there to store it. They are hard problems, but it is certainly possible. These are problems that have been fixed in other systems as well. Page is not that difficult in Postgres as it is in, say, MySQL, say, Oracle. It's certainly possible. Another item, there are various systems in Postgres which store approximations of how large a data set is or boundaries of things. In Brin, this is specifically quite interesting as well, where we have the minimum and maximum value within a range. But if you're working with strings, they can be very, very, very large. So it may not fit on the page, but we can round it up and round it down. And because the Brin index only stores summaries of the data of what might be there, we can round the string up to, say, the first 10 characters of the string, and then round it up if it is longer than that, and round it down if it's for the lower bound of the range. And so decrease the amount of data that we have to store to still have reasonably accurate data there. It's really wasteful what we all store there. We can do much better there with relatively simple modifications. It's just someone needs to do the legwork. I'll be talking about WAL now, record overhead and compression scope. They are fairly mundane subjects. So does anyone know how large an empty WAL record is? The minimum size of a WAL record? Huh?
24 bytes.
Exactly, 24 bytes, which is in these items. And well, Of those, the Excel previous, the info bits, the resource manager ID, and the CRC total 14 bytes. It's really difficult. I have not found a way to decrease that. But the length of the record is essentially always smaller than 2 to the 16 bytes. Why do we have a 4-byte value there? Because our maximum wall record size is the 1 gigabyte, which fits well in the 32 bits of the length record, of the length value. But if we're not going to use all of those bytes, we should be able to decrease the size of that. Same with the transaction ID. No index uses the transaction ID. I have checked, none of them use it. Why do we store it for the indexes? It's quite wasteful. We do compact write-out for basically all the data, but not here. It's wasteful. And lastly, we have 2 bytes of padding. And if people complain if I add a few bytes to a wall record or certain wall records, and we have 2 bytes laying around here. It's just, huh?
I can say the transaction ID has been useful for debugging when I'm looking for records that pertain to, like, I know which transaction ID caused the problem, or I know where in the log the problem happened.
Yes. Yes, I can understand why it is useful for debugging, but it is 1/6 of the overhead of a wall record, a basic wall record. It's wasteful. We can do.
Especially those small wall records.
Yeah, index insertions. They are very small already. Putting 4 bytes there, that's nearly 10% of the wall record size. That's not great. So when we modify a single page, anyone guess? How large is a wall record that modifies a single page without any data? Huh?
8 kilobytes without compression.
No,
The wall record itself, just the overhead for modifying a page. It's 44 bytes. Because you have the wall record header and the block ID, some fork flags, you have a length, the rel file locator, and the block number, which you're modifying. It's a lot.
Full page image.
It doesn't have to be there. You can just modify a page without actually storing a full page image, because the checkpoint has been a long time ago and the previous record has already written something out. Or you've disabled full page images. It's possible. Wouldn't suggest it on most file systems, but it's possible. But so the block ID and the fork and the flags is not realistically removable. Maybe with some trickery it can be reduced in size, but the length bytes, it is quite often just 0 or basically empty, especially in cross-block update records of the heap. It contains no data, it only shows that it was modified. The rel file locator are also 3 OIDs, and it can be anything, but often small when you're on a new system. We can use some better encoding schemes to make this easier to compress. The main issue here with the rel file locator, or at least that I have with the rel file locator, is that it uses OIDs, which are generated with a global OID counter, just like the toast system. The values can be anything. They can be completely random. While if we were using sequential OIDs for the database ID, for the table space ID, and for the relation ID, we would consistently know they are smaller. They are fairly small values, so we can use variant encoding when to optimize the wall size. But right now they are random. You can't rely on them being small in all systems, and you would lose a lot of performance if you started trying to compress them. But we can do better, definitely. Yeah. Then the last item in WAL is the compression scope. Right now, the only compression that we do in wall records is full page images, and only for separate full page images. If I write out, say, a range of GIN pages or a range of B-tree pages, it compresses each of them separately within its own separate compression context, and it's really wasteful. We know that pages which are written sequentially in an index are very likely to contain similar data. So if you combine them all, they should be much better compressible than you would get if you compress one of them, then the other, then the other. It's really something that could realistically be done. Someone should get to it. And maybe we could even decide to compress the full wall record data. This would mean that we would need to take more CPU time to decode the wall record, but it would also mean that our wall records would on average be smaller. Another potential here is that we could use compression dictionaries for certain wall records, but that is for now a pie in the sky. I wouldn't expect that anytime soon because we don't even have compression dictionaries for anything else yet. So. Yeah. Then the last item, Toast. I'll be talking a bit about compression and about updates. Right now our compression is for every value, it compresses the data using a generic algorithm. It works, it's fine, but it doesn't do nearly as good a job as certain optimized and type-aware compression algorithms do. There have been threads on the list about improving this. Specifically, someone suggested to use compression dictionaries, but we hit issues there with the toast pointer not having enough data to also allow a compression dictionary ID. Because every time you create a new register a new compression dictionary, you cannot ever drop that, and you need to have that specific version to decompress the old toast data. And it's really difficult to determine which are still in use. So it needs to be, for compression dictionaries to actually be implemented in a way that makes sense and is dynamic enough. We need versioning, we need analysis. It has been analyzed. There are threads on the hackers list about this, but we've had some issues there, which still need to be solved. Another one is also data type aware compression. Right now we have 3 generic compression algorithms. Certain types have certain better compression algorithms available when you know it works better. For instance, differential encoding for integer arrays. If you know your integer array is already sorted, you could probably and if you could register that you would like to compress this the toasting regulate the toasting of that column with differential encoding, you could probably get much better compression performance than what you get with, say, libc, zlib, or the PG native compression systems. One issue with that is, this would probably require new create type hooks, which I'll also talk about in the next slide. If you update the large toasted value, it can create a lot of data because it rewrites the whole value right now. So your wall volume is huge. Your OID churn is huge at a large size because every value gets a new OID. And the toast table bloat is also huge because you duplicate the value every time you update it, and all of the values. So someone noticed this and asked, why do we not have a specific API for updating, say, byte arrays for appending values to byte arrays, or update a JSONB key value, or that kind of stuff. The API, yes?
The API, you mean a wall log record, or what do you mean API?
The internal systems to update a toast pointer to point from one value to another which has the additional data or the changes. Because right now you slice and dice a toast value into similar sized chunks based on I have 10 megabytes, I slice it in, I compress it and then slice it in 2 kilobyte chunks and store that in the database. But if you add a 0 byte, all you really would need is to append a 0 byte to that compressed data, which is basically only the last.
Didn't you just lose MVCC entirely? You can't simply update in place because you don't know if you're going to.
You don't need to update in place, but you only need to update the last slice of the data.
So you could have the old and new version of the last slice, but not update all the other slices.
Just chunks.
It would
Yeah,
change
chunks.
the way the visibility
Yeah,
lifetime
I mean,
works
right
on
now
the
we don't
chunks
really
now.
track visibility of toast chunks, so there would need to be some thought about how to make that work.
Yes, there needs to be an API to make that work. There is a thread about extending toasting for types. My last comment on that was basically a type needs to have its own awareness about how to slice and dice its chunks, because JSON values can be considered similar to a row, and we don't rewrite a whole row every time a row is updated. Only the updated values are stored in the wall, and only the updated values are retoasted when we toast the data. If we made a type aware of how to or made the toast system aware that types can also be composite values, and make the types handle their updated values in the toast system, we could reduce the wall, we could reduce the churn in toast tables, as well as allow the types to more efficiently access their composite values when not all the data is required. And that's basically what I had for you today. If you have any questions, please go ahead. If you don't have any questions, then hit me up or that. I am planning to have the PG Node 3 stuff ready in a few weeks. I don't know when quite yet, but yeah. Any questions?
For JSONB columns,
Yes.
you have a lot of shared keys across rows. You talk about ways to duplicate or replace. Like, I don't want to write something, but is there any thoughts on?
What would work well, what probably would work best there is having a compression dictionary there which contains the information that those keys are common. So that when you apply that dictionary within the when you use that dictionary while compressing, it would be able to better compress the data than when it didn't have the context of, hey, I have a lot of those keys. Does that answer your question?
Yeah, I mean, I can write a function to do that on the indexing as well as on the write messages. Like, I'd have to cover all the bases to store out that dictionary. So if I have first name, last name, I'm going to convert that to A and B.
Yeah.
And store it as A and B, the JSONB. But now I've got to make sure when I do a JSON path query that I've got to look for A and B so that the index hits.
I think how this would work is during the compression phase of data, of toasted data, this would be replaced. But that is, once detoasted, it would still be the normal JSONB. So all the operators would still use the same data as it would normally. It's just that when on disk, when compressed, it's less data because it knows what kind of dictionary it had to use.
Okay, so you're saying it'd be more of a
Alternate compression.
alternate compression of this.
Not JSON-B specific, because you could apply the same thing to byte arrays, texts, that kind of stuff. It doesn't have to be JSON-B specific here. It's just that the analysis needs to be somewhere. And if I mentioned here, data type aware compression is more based on the notions of the internals and using that. When you apply dictionary compression, what I meant was using the dictionary capabilities of the existing compression methods. For instance, LZ2, I think, allows you to supply a dictionary of what am I. This is the context of already. This is the data that you should expect, and use that as a dictionary for the data. I think definitely. I don't know. We have at least one of those algorithms already in place. It's just that we don't have the information of. We don't have the space to store the information of which dictionary are we using. So that needs effort. Yeah.
You mentioned compressing full-page images together. Of course, I'm working on this right now, but I'm working for like a few months because it touches a lot of code in different places. The most usual case for this is B3 compression, because otherwise we usually have just one FPI.
Yes.
And there is it's not just about savings of wall, it's also about saving CPU, because when we restart compression on each page, we reinitialize codec again, and it allocates some memory for lookup tables. And well, I expect this to finish July Confest.
Looking forward to that. Any other questions? Well then, thanks.